So for this session, we now go to section 1.3. It's matrices and matrix operations. Okay. So in the previous lectures, we already introduced some matrices. Okay, and we called it the augmented matrix. Okay, so in this lecture, we will formalize what a matrix is, and then we will introduce the operations used on the set of matrices. Okay, so a matrix, it's a rectangular array of numbers. Okay, just like what you've seen in the augmented matrix. The numbers in the array, they are called entries of the matrix. So for example, these are all matrices. Okay, so in this matrix, you have two rows and then you have three columns. Okay, rows, they are horizontal. Columns, they are vertical. Okay, so in this example here, you have four rows and then you have also four columns. In here, you have four rows and one column, while on this example, you have one row and then you have four columns. Okay, so these are all matrices. Now, if a matrix has m rows and n columns, we say that the matrix has size m by n, and we write it m times n here. So if we go back to this example, we usually write the size as a subscript of the matrix. Okay, so we usually write it this way. So this has two rows and three columns. So you have here 2 by 3. So it's read 2 by 3. Okay, or 2 times 3 if you wish. This guy here, you have 4 rows and 4 columns. This is 4 by 4. In here, you have 4 rows and 1 column. So you have 4 by 1. In here, you have 1 row and 4 columns. So you have here 1 by 4. Okay? So that's the size of a matrix. Now, a matrix with only one row, it's called a row vector. And a matrix with only one column is a column vector. So this guy here, this is a column vector. Okay? Because you only have one column. While this guy here, this is a row vector because you only have one row. Then, a matrix is denoted by uppercase letters. The entries are denoted by lowercase letters. So for example, if we have here an m by n matrix, then we write it this way. So the name of the matrix for this, it's capital A. And the entries, okay, we use the lowercase corresponding to the uppercase. So capital A in here, the entries will be lowercase a also. But keep in mind, we have written here some subscripts. So remember the augmented matrix, okay? We also had subscripts there, okay? So for example, in here, we have A11. This is not A11. This is A11. And then here you have A12. And then here you have A1N. Here you have A21, A22 here, and A2N, and etc. and etc. And of course, the subscripts here, they tell you the location of the entry. Okay? So the symbol Aij, we mean it's the entry at row I and column J. Okay? So for instance, if your row I is somewhere here, row I is somewhere here, and then your row J or your column J, it's somewhere here, then this guy here, the guy here is your entry Aij. Okay? So the symbol Aij, we mean the entry at row I and column J. So if you want, entry on row M and column 2, okay, then this is this entry here. You're on the row M and then you are on the column 2. Okay? Now, here are some other notations that we will use. Suppose we didn't use capital letter to name a matrix. We can just write it this way. So we have these square brackets and then Aij, and then here you have your M times N. So this guy here, it's an M by N matrix. Okay? And since the entries here, your Aij, it's a small letter A, it will be obvious that the name for this matrix, it's capital A. Okay? Well, of course, you can use a different name for that. But the way we do it, or the way we write it, okay, at least in our course or commonly or as a convention, okay, the letter used for the name of the matrix will be the same letter used as the entries of the matrix. Okay? One is uppercase, that's for the name. For the lowercase, that's for the entries. Okay? And if we know the size, or if we don't really care about the size, then we can just remove this M by N. So we simply write this, square bracket Aij. Okay? Now, if A is a matrix, then this guy here, so parenthesis A, and then there's a subscript Ij, this is the entry Aij. Okay? So notice in this notation, we use the entry Aij. We enclose it inside a square bracket or square brackets. Okay? Then we say this is the matrix. On the other hand, we have a matrix here. We don't know the entries yet. Okay? Then if we want to call the Aij entry of that matrix A, we can just write this guy here. Capital A, that's the name of the matrix, and close it inside parentheses, and then put the subscript Aij. Okay? But anyway, in this course, most of the time, I'll be using this symbol as the entry for the matrix. Okay? Now, if a matrix is a row or column vector, we use boldface, lowercase letters for the name of the matrix. And the entries will just have one subscript. Because, well, for example, this guy here, it's a row vector. You know that there's only a single row. So you don't have to put the subscript for the row. Which means this is your row vector A. So it's boldface lowercase letter. Okay? And it's equal to this row vector. So the entries are A sub 1, A sub 2 until A sub n. Okay? Here, we have a column vector. Okay? So we use small letter, bold face, B for the name of this column vector. And the entries are B1, B2 until Bm. So again, single subscript. It's because we know that the column is just one. So we don't have to put that. Okay? So this is only for the case column vector or row vector. Questions? Now, if the number of rows and columns are the same, then what we have is a square matrix. Okay? For example, in here, you have A11, A12 until A1n, and then going down, we have A11, A21, AN1. So the number of rows is also n. The number of columns, it's also n. So you have a square matrix. So in this guy here, this is a square matrix. 4 rows and 4 columns. Okay? Questions? Now, for a square matrix A, the entries A11, A22, ANN, they are said to be in the main diagonal. So the entries here, okay? The entries that you see here are on the main or in the main diagonal. Okay? Now, let's look at some relations on matrices and also operations used on matrices. Let's define equal matrices. So two matrices are equal if they have the same size and their corresponding entries are equal. So equal matrix. For example, you have here matrix A, you have here matrix B. So the size of A here, you see you have M rows and N columns. So the size is M by N. On the other hand, for the matrix B, you have M tilde. So M tilde rows and then N tilde columns. So the size of this matrix B, it's M tilde by N tilde. Okay? So for now, they look like different. Okay? But we say that these matrices A and B are equal if the number of rows are equal. M equals M tilde. And also, the number of columns are equal. N equals N tilde. That's your same size condition. And furthermore, the entries, the corresponding entries must be equal. Meaning, your Aij must be equal to Bij for all I and for all j. Equal entries. So that means this entry here and this entry here, they are equal. This entry here equals this entry. This entry here is equal to this entry and etc. And all the entries. Okay? So equal entries. So matrices are equal if they have the same size and their corresponding entries are equal. Okay? For example, we want to find the values of x and y so that these two matrices are equal. So observe our condition so that they will be equal. Okay, same size. You have here 2 rows and 2 columns. So this is a 2 by 2 matrix. Your matrix B, it's 2 rows and 2 columns. 2 by 2 matrix. So they have the same size. Now, we need to check the next condition. They must have the same entries, or they must have equal entries. Okay? Or corresponding entries must be equal. This means this is your A11 entry. This is the A11 entry of B. So A11 entry of A, A11 entry of B. This means that your x plus y, this must be equal to -1. So x plus y must be equal to -1. This entry here equals this entry. They are both 2. This entry here and this entry here, they are also the same. They are both -1. This guy here, you have x minus 2y. It must be the same as this entry, which is 3. So we should also have x minus 2y equals 3. So we need to solve for x and y if there is a solution. And once we have that, then we will get the values for x and y. Once we have a solution for this and we found that out, then we are done. And to do this, well, two equations, two unknowns. Okay? If this is your equation 1, this is your equation 2, we can just do elimination method, or we can use the method that we have learned in the past lessons. Okay? But anyway, two equations, two unknowns, so this is easier to do. So what we can do here is to subtract equation 1 minus equation 2. If we do that, we have what? X minus x, that's 0. Y minus -2y, that becomes 3y. -1 minus 3, that's -4. And therefore, y equals -4/3. Correct? And then we have a value for y. We substitute this. Substitute in equation 1. We have x plus y equals -1. This gives us x equals -1 minus y. But y, it's -4/3. So this is -1 minus -4/3. And this will be equal to 1/3. Okay? So x equals 1/3. And we now have the value for x. If you check it here, you will get what? 1/3 minus 4/3, that's -3/3, that's -1. In here, you have 1/3 minus 2 times -4/3. So that becomes 1/3 plus 8/3. And that becomes 9/3. Or that's equal to 3. So these are the values these are the values needed so that we'll have equal matrices. Okay? Questions? Now, let's start with some operations. So suppose we have two matrices, A and B, that have the same size. They must have the same size for this operation sum and difference to work. Okay? So we define the sum A plus B. Okay? So this is the matrix C. Of course, the entries will be Cij since we use capital C, where the Cij is equal to Aij plus Bij. This means that you add their corresponding entries. Okay? A11 should be added to B11. A12 should be added to B12. Okay? Aij should be added to Bij. And that's why we need these two matrices to be of the same size. Okay? The difference, A minus B, so it's a matrix C with entry Cij, where Cij is just the difference, Aij minus Bij. So entry-wise subtraction. So same as the sum here, entry-wise addition. Here we have entry-wise subtraction. The third operator here, it's called the scalar multiplication. So what is this? If R is a scalar, we call it a scalar. It's just any real number in our case. Okay? In our case, it's just any real number. So if R is a scalar, then the scalar multiple RA, so R times A here, this is the matrix C with entry Cij, where Cij, this is equal to RAIJ. This means that you just multiply this number R to all the entries of A. Okay? So sum, you add entry-wise. Difference, you subtract entry-wise. Scalar multiplication, you multiply the scalar to all the entries of the matrix. Let's look at the example here. Suppose we have this matrix A and matrix B. We want to calculate 2A minus B. So let's start with this guy here. This is a scalar multiplication. This is a scalar multiplication. And once you know that one, you can do the difference. Okay? So I'll do this step by step. I'll start with 2A. So 2A, it means we just need to multiply 2 to all the entries of the matrix A. So 2 times 1, that's 2. 2 times 3 here, that's 6. 2 times negative 1, that's negative 2. For this, you have 2 times 5, that's 10. 2 times 2, that's 4. And then 2 times 3, that's 6. So notice, this scalar is multiplied to each of the entry of A, and the location is on the same location as in this guy. So 2 times this guy here, A11 entry, the 2 goes to the 11 entry also. If 2 is multiplied to this A23 entry, okay, so 2 times 3, that's 6. The 6 is also on the 23 entry of 2A. Okay? So what about 2A minus B? So for this, let me write this. 2, 6, negative 2, 10, 4, 6. We subtract matrix B. So we have here minus 1, 2, 1, 2, 3, minus 3. So entry-wise subtraction, we have here 2 minus negative 1. So 2 minus negative 1. 6 minus 2. 6 minus 2. Negative 2 minus 1. Negative 2 minus 1. Here we have 10 minus 2. 10 minus 2. And then we have 4 minus 3 here. 4 minus 3. Then lastly, you have 6 minus negative 3. 6 minus negative 3. Okay? And then if we simplify this, we have, so 2 minus negative 1, that's 3. 6 minus 2, that's 4. Minus 2 minus 1, that's minus 3. Here you have 10 minus 2, that's 8. 4 minus 3, that's 1. 6 minus negative 3, that's 9. So this is the answer to 2a minus b. Okay? Another example here, we have a plus 3b. Okay? So some students will do this. They'll just write everything at one shot. So we have a plus 3b. So this is equal to a, it's 1, 3, negative 1, 5, 2, 3. And then plus 3 times the b. Minus 1, 2, 1. And then 2, 3, negative 3. It's totally fine. Okay? So let's just calculate this. We have here 1, 3, negative 1, 5, 2, 3. Then plus. We have here 3 times negative 1, that's minus 3. 3 times 2, that's 6. 3 times 1, that's 3. 3 times 2 here, that's 6. 3 times 3 here, that's 9. And then 3 times negative 3, that's negative 9. And then they just add. Okay? You have 1 plus negative 3. I'll write the answer here. So that's negative 2. 3 plus 6, that's 9. Negative 1 plus 3, that's 2. 5 plus 6, that's 11. 2 plus 9, that's another 11. Then 3 minus 9, that's minus 6. So this is the final answer. Okay? So addition and scalar multiplication or subtraction, they are easy to solve. Okay? They are easy to work on. Now, this a plus 3b and 2a minus b, they are called linear combinations of a and b. Okay? They are called linear combinations of a and b. And in general, if you have A1, A2 until AR, these are matrices of the same size. And then you have some numbers C1, C2 until CR. Then this sum here, C1 times A1 plus C2 times A2 plus until CR times AR. So this is a scalar multiplication. This is also a scalar multiplication. This is also a scalar multiplication. And then you add them. Okay? So we call this sum here a linear combination of A1, A2 until AR. And C1, C2, and CR here, we call them coefficients. Okay? So C1, A1 plus C2, A2 plus until CR, AR, it's a linear combination of A1, A2 until AR with coefficients C1, C2 until CR. Okay? Questions so far? Now, we define product of two matrices. And please listen very carefully because multiplication of two matrices is not as easy as the addition or subtraction or scalar multiplication. Okay? First, let A to be an M by K matrix and B to be a K by N matrix. Okay? So let's start with that. A, it's an M by K. And then B, this is a K by N matrix. We define the product AB. So A times B. So it's the matrix C, okay, with entry Cij with size M by N. So if you multiply these two guys here, okay, if you multiply these two guys here, the product AB will have size M by N. Okay? It's like when you combine these two guys here, M by K, K by M, the K disappears and you will get M by N. Okay? Now, what does this mean? K, it's the number of columns of A. B, or K here is also the number of rows of B. So you can multiply two matrices if the left factor, okay, if the left factor or if the number of columns of the left factor is the same as the number of rows of the right factor. Okay? So left factor, okay, number of columns equals right factor number of rows. Okay? You can multiply them. Okay? The next question is, how are you going to multiply? You have here the entry Cij. It will be A1, AI1, B1J plus A12, B2J plus until A1K, BKJ. Okay? It's not easy here, but say, for example, this is your matrix A. This is your matrix A. And this is your matrix B. Okay? You look at the column. Take note. A, you have the Cij, you have here AI1. Okay? So this AI1, it's the entry on the ith row, first column. Okay? So say this is your row I. So you have here your AI1, AI2, AI3. 3, etc. until A, I, K. Take note until A, I, K because A has K columns. Column 1, column 2, column 3 until column K. Okay, suppose this is your row I. And then suppose this is your column J. Column J. It's somewhere here for the B. If this is your column J, then you have here B1J, B2J, B3J, until BKJ. And take note, the first subscript here, the last entry for matrix B, it's K. Because because B has K rows only. Okay? And what is this? Number of columns for A equals number of rows for B. Okay? Then you multiply correspondingly. Okay? This guy here, it's being multiplied to this guy. This guy here, it's being multiplied to this guy. This guy here being multiplied to this guy. And this guy here, etc. being multiplied to this guy. That's your this. This until this. And once you do the multiplication, you add all of them. Okay? And this will become your matrix C. Okay? And that's just your Cij. When you add them, after multiplication, you add them, you'll get this single entry on the right-hand side. Okay? Ij for the subscript of C, that's coming from row I of A and and column J for B. Okay? So that's multiplication of matrices. Let's apply this to actual matrices here. So again, condition. The number of columns for A must be the same as the number of rows for B. Okay? The number of columns of the left factor must be the same as the number of rows of the right factor. Let's look at this. A here, it's 2 by 3. 2 rows, 3 columns. M here, okay, M here, it's 3 rows by 2 columns. Left factor, it's A. Right factor, it's M. Okay? So, AM, okay? This is 2 by 3, and then M, it's 3 by 2. So, the product will have size. So, remember this guy? It's like you are removing the K, the one in the middle here, and you'll be left with the outer numbers here. So M by K, M by N. So in here, we drop this 3 here, we'll be left with this 2 by 2. Okay? So the product is or has size 2 by 2. Okay? So we expect a 2 by 2 matrix after multiplication. Now, the actual multiplication here, you have 1, 3, negative 1, 5, 2, 3. We multiply this to the matrix 1, negative 2, 5, negative 1, negative 2, 3. Okay? So, first, let's look at this entry here. We say it's a 2 by 2 matrix, correct? So let us look at the C11 entry or the 1-1 entry here. Okay? Let me just put it here. This is the column 1. This is your column 2. Here is your column 2. And then somewhere here, this is your row 1. And then somewhere here, it's your row 2. Okay? The row entry here, they will be the row of the matrix A, the row of the left factor. The column entry is the column for the matrix for the right factor. Okay? So actual multiplication, let's start with first row of A and then first column of M. Okay? So first row of A and then first column of M. So you have here 1 times 1. So I'll write this completely. 1 times 1 plus 3 times 5. Okay? 3 times 5 plus we have here negative 1 times negative 2. So negative 1 times negative 2. So I think I have to adjust this column 2. So this is for the rows. And then this guy here, let me put it somewhere here. Okay? So this is for this guy here. First column, first row of A, first column of M. Okay? Now, let's look at first row of A and then second column of M. So first row of A and second column of M. That will be on this entry. First row of A, second column of M. So we will have 1 times negative 2. So 1 times negative 2 plus 3 times negative 1. 3 times negative 1 plus negative 1 times 3 plus negative 1 times 3. Okay? Negative 1 times 3. Okay? So first row of A, second column of M. Now, let's look at second row of A and then second column of M. So the location will be this, row 2, column 2. Correct? Second row of A, second column of M. Row 2, column 2. So we have here 5 times negative 2. So 5 times negative 2. 2 times negative 1. 2 times negative 1. And then we have 3 times 3. 3 times 3. Okay? And then finally, Let's look at second row of A, first column of M. So second row of A, first column of M. Second row of A, first column of M. So this is where we will put the product and sum. So we have here 5 times 1 plus 2 times 5 plus 3 times negative 2. 3 times negative 2. Okay? And then finally, you'll just need to simplify all of these products and sum. So if we simplify this, we will have here 1 times 1, that's 1, plus 3 times 5, so 1, plus 15 plus 2, so negative 1 times negative 2. For this, you have 5 plus 2 times 5, that's 10, plus 3 times negative 2, that's negative 6. For this, we have negative 2, negative 3, negative 3. And then for this, we have negative 10 minus 2 plus 9. Then finally, we will have 1 plus 15 plus 2, that's 18. Minus 2 minus 3 minus 3, that's minus 8. 5 plus 10 minus 6, that's 9. Minus 10 minus 2 plus 9, that's minus 3. So this is the product, AM. Okay? Questions? Next example, BM. We want to find the product BM. Okay? So let's see. BM, this is equal to, let us just copy B. Negative 1, 2, 1, 2, 3, negative 3. And of course, M is the same as the one in the previous slide. 1, negative 2, 5, negative 1, negative 2, 3. So take note, this is still 2 by 3. This guy here, it's 3 by 2. So the product will be 2 by 2. Okay? So what is this? So this guy here being multiplied to this. Okay? So we have here negative 1 times 1. I'll write the product already. That's negative 1. 2 times 5, that's 10. So plus 10. 1 times negative 2, that's minus 2. Okay? So first row, first column. Let's look at first row, second column. So this guy now. First row, second column. So it should be on the first row, second column entry. So negative 1 times negative 2, that's positive 2. Plus 2 times negative 1, that's negative 2. Plus 1 times 3, that's 3. Okay? And then Now let's look at second column for M and then second row for B. So second row, second column, so it must be on the 2-2 entry, row 2, column 2 of the product. So this part here. Then we have 2 times negative 2, that's negative 4, plus 3 times negative 1, that's negative 3, plus 3 times 3, that's negative 9. And then finally, we have this guy here. Okay. Second row, first column. So second row, first column, it's on this part. We have 2 times 1, that's 2. 3 times 5, that's 15. Negative 3 times negative 2, that's 6. Okay? And then finally, we'll just need to simplify. Negative 1 plus 10 minus 2, that's positive 7. 2 plus negative 2 plus 3, that's 3 here. 2 plus 15 plus 6, that's 23. Negative 4 plus negative 3 plus negative 9, that's negative 16. So this is the product BM. Okay? Questions? Now, for this example, I will not put this on record. So if you are rewatching right now, you can just work on your table again or workspace. So some remarks, okay, on about the operations on matrices or the operators on the space or the set of matrices. Two matrices can be added if they have the same size. Okay? Two matrices can be added if they have the same size. Next, two matrices can be multiplied if the number of columns of the left factor is equal to the number of rows of the right factor. Okay? Now, we have, say, A, size is M by K. B, size is K by N. The product AB is defined, and the size will be M by N. What if you interchange them? B, A, but the size of B it's K by N. The size of A it's M by K. And suppose N is not the same as M. Then this guy here is not defined. You cannot do any multiplication for that. So, from here, you can say that AB is not necessarily the same as BA. Because on the left, multiplication is defined. On the right, it's not even defined, possibly. Okay? Even if, say, you have this guy here, okay? you have A, okay, N by K, okay, and then B, it's K by N, but A here, it's not the same as K, okay? The product AB becomes what? N by N. On the other side, you have your B. Again, it's K by N. A, it's N by K. So if you multiply them, BA, the size will be K by K. But N is different from K. Therefore, AB and BA have different sizes. So, you can also say they're not equal. In fact, they will not be equal because they have different size. By definition, two matrices are equal if they have the same size and entry-wise are equal. But since they already have different sizes, they can never be equal. Okay? So in general, we have this. AB is not necessarily the same as BA. Of course, there will be cases where AB equals BA. There are some matrices, set of matrices, when you multiply them, they will be the same. We will look at those matrices later in the course. But in general, AB is not necessarily equal to BA. Okay? Because maybe the product AB is defined, the product BA is not. Or the product AB have the same, have different size as the product BA. And in fact, even if they have the same sizes, the product AB has the same size as the product BA, it's possible that the entries are not the same. So there's a lot of factors to consider. Okay? Now, a matrix can be partitioned or subdivided into matrices or blocks. So what does this mean? Suppose you have this matrix a 3 by 3 matrix, okay? You can partition this in the following manner. So you have this submatrix here, it's a 2 by 2 submatrix. You have this submatrix here, it's a 2 by 1 submatrix. It's a column vector here. This matrix here, it's a row vector. It's a 1 by 2. And this matrix here, it's a 1 by 1 matrix. Okay? So A is partitioned into this. And you can write A as follows. Capital A11, A12, A21, A22. So it looks like it's a 2 by 2 matrix. But the entries of this matrix here are also matrices. A11, it's this matrix here. A11, A12, A21, A22. A12, it's this column vector here. So A13, A23. A21, it's this row vector here. A31, A32. And capital A22 here, it's this matrix here, A33. Okay? So your matrices, they can be partitioned into blocks. Okay? So the matrices A11, A12, A21, A22 with capital letter A, they are called submatrices of A. Okay? Submatrices of A. And I have I have used this term before when we were dealing with augmented matrices, okay? When we do Gaussian elimination. So this is not new to us. Now, if we write A as rows, then your A can be partitioned into this. So row 1, it's A11, A12, A1n. Row 2, A21, A22 until A2n. Row M, it's AM1, AM2 until AMN. Then we can rename this row 1 as R1, this row 2 as R2, this row M as RM. So it looks like your A is a column vector, but the entries of that column vectors, okay, are actually row vectors. If we write this by column, so we look at column 1 here, column 2 here, until column M or column N, then this matrix A is like a row vector, but the entries of the row vector is actually a column vector. Okay? So, suppose we have here A. It's written this way. So, take note, boldface A, entries of capital A. So, meaning, this A here, it's a row vector. This A here, it's a row vector, etc. And then we let capital B to be this guy here. It's a row vector, but the entries are actually column vectors. And then the number of columns of A equals the number of rows of B, which is equal to R. Okay? So it means, for example, your A1, the vector A1, okay? This is what? A11, A12, until A1R. Because the number of columns of A is equal to R. While for B, the number of rows of B is also equal to R. So this say B1 here. This is a column vector. This is B11, B21 until BR1. Okay? So number of rows of B equals the number of columns of A. Then we can talk about multiplication. The product AB, it's your matrix A times this column vector or this row vector B. So it's like we are just going to distribute the A. So here you have a B1, a B2, a BN. Or you can also have AB here. Okay? We now write A as a column vector whose entries are row vectors. You multiply it to B. Then it's like you just distribute the B inside. So A1B, A2B until AMB. Okay? So, for example, you have this. Let us work on AM. Okay? And we write A or we write M as column vectors. Sorry, we write M as a row vector whose entries are column vectors. So In this example, this guy here, this is your M1 and this is your M2. So this is your M1 and this is your M2. So if we follow this, what will happen? You have your AM, AM. This is equal to A times M1, M2. So this is simply A, M1, A, M2 based on this equality. But now let's bring M1 and M2, the entries of M1 and M2. This will be what? A, M1, it's 1, 5, negative 2. And then you have here A, then your M2, that's negative 2, negative 1, 3. So your A here, it's being multiplied to a single column. Here, your A is being multiplied to a single column. So it's like we have something like this. If we bring back your A here, you will have 1, 3, negative 1, 5, 2, 3 being multiplied to the column 1, 5, negative 2. Then for this guy, we have 1, 3, negative 1, 5, 2, 3. And then we are multiplying it to the column negative 2, negative 1, 3. Okay? And then you have here 2 by 3. Here you have 3 by 1. So multiplication is defined or well defined. 2 by 3, 3 by 1. Okay? So if you multiply this, so you have what? 2 by 3. The other guy, it's 3 by 1. So when you multiply them, you will end up with 2 by 1. Same is true with this. You have 2 by 3 here, 3 by 1. So when you multiply them, you'll end up with 2 by 1. So try to work on this. Okay? You should end up with the same answer as in before. Okay? So try to work on this and check your final answer with the one we had earlier. So this is for this way of multiplication. Let's look at this way of multiplication. So BM, we write B as a column vector whose entries are row vectors. Then we multiply it to M. So it's like we are distributing M inside this column vector. Okay? So in this example here, this guy, okay, this is like your B1 here, and then this is your B2. Okay? So BM, you have here B1, B2, then you multiply M. We have here B1M, B2M. If we put now what B1 is and what B2 is, it's like we will have this guy here, negative 1, 2, 1, multiplied to M. Then here we have 2, 3, negative 3, multiplied to M. Okay? And then you now put your M. This is your M here. So we will have something like this. For the first, we have negative 1, 2, 1. Then multiply m. It's 1, negative 2, 5, negative 1, negative 2, 3. And then down here, we have 2, 3, negative 3 multiplied to m. 1, negative 2, 5, negative 1, negative 2, 3. Okay? So now, this guy here, we have 1 by 3, one column, one row, 3 columns. And then the m here, it's 3 by 2. So if you multiply, it will become 1 by 2. Similarly for this will be 1 by 2. This will be 1 by 2. Okay? So you will end up with the same matrix as in before. Okay? So, a question, can you do this? Can you use this? Or can you just use the actual definition? Yes, of course, you can use this if you want. But most of the time, it's safer if you use the actual definition. Okay? So most students will use the actual definition. Okay? Now, let us continue with this theorem. Let A be an m by n matrix and let X be an n by 1 column vector. So you have this. Okay? Then this matrix equation, AX, or this matrix here, AX, it's equal to this guy. Okay? So it's like you have this column for A, you multiply it to the first entry. So first column of A, multiply it to the first entry of X. Plus the second column of A, multiply to the second entry of X. Plus etc. This last column of A multiplied to the last entry of X. Okay? So X here, X1, X2 until Xn, they are all scalars. So you can actually bring them inside this guy here or inside this guy here or this guy here. And therefore, if you have this a column vector plus a column vector plus a column vector, if you add them, you will still get a column vector. Okay? It's just that, what is this? It's like a linear combination, okay, of the columns of A. So AX, it's like a linear combination of the columns of A with coefficients x1, x2 until xn. Okay? So later in the course, we will see this guy here. So towards the end of the course. But we will use this somewhere in the middle. Okay? Between now and that particular topic that I was talking about. But let's see how this one is proved. So you start with AX. You have this matrix, and then you have this column vector. Okay? So you can do the multiplication. So first column, first row multiplied to the column, second row multiplied to the column, etc. Last row multiplied to this column here. So if we do that, we have here a11 times x1 plus a12 times x2 plus a1n times xn. So you have this first row, first entry here. Second row multiplied to the column, you will get the second entry. Last row multiplied to the column, you will get this last entry in here. And then this is a column vector because this is a single number here. You are adding them. This is also a single number. And this is also a single number. So it's just a column vector. Okay? And then you can separate. You have these pluses. You separate them in such a way that on one column, you have the x1. On another column, you have only the x2. Okay? On another column, you only have the x3 until this last column here. So you will have this a11x1, a21x1 until am1x1. So this is your first column here. Okay? This guy here, it's this. And then this guy here, it's this guy here, etc. Okay? But you have x1 on this entry, you have x1 on this entry, you have x1 in this entry, you can bring it out. Scalar multiplication. Also this, you have x2 on this entry, x2 on this entry, all throughout x2 on the entry, you can bring it out. Scalar multiplication. And that will be true for each column vector that you will see in this sum. And therefore, you will end up with this. Okay? So this is the proof of this theorem here. Of this theorem here. Okay? Questions? Now, some more. Suppose you have your matrix A written as a row vector where each entry is a column. And then the matrix B written as a column vector where each entry is a row vector. Then we can still have this definition. The product AB, it's like entry-wise multiplication. So A1B1 plus A2B2 plus until ARBR. This is called the column row expansion of the product AB. Okay? So again, if you try to study this, okay, you will find this helpful. If not, just use the definition of matrices or multiplication of matrices. Okay? Now, how are we going to use this concept of matrices? We formalize the definition of matrices. We have addition, subtraction, scalar multiplication of one scalar with a matrix, and then we do multiplication of matrices. So how are we going to use them in that, or how are we going to connect them with the topics that we have discussed in the previous lecture? So let us go back to linear systems. Okay? So we have a linear system here. A11x1 plus A12x2 plus until A1 and xn equals B1, etc. We can rewrite this into a matrix equation. So we set capital A to be this matrix, A11, A12 until A1, A21, A22 until A2n, AM1, AM2 until AMN. This guy here, this matrix here, we call this the matrix of coefficients. Now, we put the variables x1, x2 until xn. We put it, or we put them into a single column vector. Let's just write it as the vector x. And of course, the constant parts, b1, b2 until bm, we just put it also into a single column vector. And we write it as vector b. Then this linear system, okay, can be written in matrix equation form. So AX equals B. Matrix A multiplied to vector X, that's equal to vector B. And as I have said, this matrix A, it's called the coefficient matrix of the linear system, or the matrix of coefficients of the linear system. Okay? Questions so far? Now, let us look at some more operators on the matrices. So let A be an m by n matrix. The transpose of A, which we denote by this. You have A here and then a superscript T, capital T. Okay? So this is the matrix n by m with entries given by this. The entry, the Aij entry of the transpose of A, it is the Ji entry of A. Okay? The Ij entry of A transpose, it's the Ji entry of A. So take note, the matrix A has size m by n. The transpose will be a matrix with size n by m. So they will interchange. The entries of the transpose is given by this. Okay? So for example, you have this matrix A, you have this matrix M, and matrix C. The transpose of A, the Aij becomes Aji. Sorry, the Aij entry of A transpose, it's the Aji entry of A. To be more to be simpler, the columns become rows, and the rows become columns. So this row 1 here will become column 1 of the transpose. So this guy here, you have A11, A12, A13, A14. So row 1 becomes column 1 of the transpose. Row 2 of A becomes column 2 of the transpose. Okay? That's the transpose. Let's look at M transpose. M, 3 by 2. Transpose will become 2 by 3. I did not mention that here, but that is the case. A, it's 2 by 4. Transpose, it's 4 by 2. So A, it's 2 by 4. The transpose, it's 4 by 2. M transpose, the rows of A or of M become the columns of M transpose. So row 1, negative 2, it becomes the column 1, negative 2 for that transpose. Row 5, negative 1, it becomes the column 5, negative 1 for the transpose. Row negative 2, 3, it becomes the column negative 2, 3 for the transpose. So 2 by 3. If you have a column vector, the transpose becomes a row vector. So this is just 1, 2, negative 2. Okay? So transpose. Rows become columns. Columns become rows. Okay? Some more operators here. Trace. Let A be a square matrix. So we want here our matrix to be square. The trace of A, which is denoted by this, TR and then A, this is the sum of the entries in the main diagonal. Okay? The trace of A is the sum of the entries in the main diagonal of A. So for example, in here, you have the matrix A here. It's 4 by 4. It must be square. Okay? So, trace of A, this is our matrix A. The main diagonal, it's this. A11, A22, A33, A44. So the trace of A, you just add them. So A11 plus A22 plus A33 plus A44. Trace of A. Trace of B. This is your matrix B. This is 2 by 2. And this is the main diagonal. So trace of B, it's just 1 plus negative 1. And this is equal to 0. Let's look for trace of B transpose. So for B transpose, let's start with that. The rows of B become the columns of B transpose. So this one here, it's 1, negative 2. And then here you have 5, negative 1. And therefore, the trace of B transpose, this is the main diagonal for the B transpose. this is 1 plus -1, and this is equal to 0. Okay? In fact, if you have a square matrix, the trace of that matrix will be equal to the trace of the transpose of that matrix. The entries in the main diagonal of your square matrix will be the same as the entries in the main diagonal of the transpose. Okay? So if you have a square matrix, the main diagonal or the entries of in the main diagonal of that matrix will be the same as the entries in the main diagonal of the transpose of that matrix. Okay? So I'll just have this um, two more examples. This guy here and also this guy here. Okay? So I will solve these two examples here and this guy here of the record. Okay? So that's the end of today's session. Thank you for staying, and I hope you've learned something today. So again, thank you